What if I told you that right now, in laboratories across the world, scientists have stopped talking about warp drives as science fiction and started treating them as a legitimate physics problem? Not something that might exist, but something we're actually learning how to build. Here's what will blow your mind. In 2024, breakthrough research has revealed that warp bubbles, genuine, mathematically valid ways to distort spacetime and travel faster than light itself, aren't just theoretically possible. They're showing up in actual experimental data. And today, I'm going to show you exactly what physicists discovered, why it changes everything about how we understand reality, and why this might be the most important breakthrough you've never heard about. But before we dive into how we're literally learning to bend the universe, I need you to do something for me right now. Hit that subscribe button, because in the next few minutes, I'm about to tell you things that will completely rewire your understanding of physics, space, and what's actually possible. And honestly, you'll want to be part of this conversation as we uncover more. Also, drop a comment right now and tell me, what country are you watching from? And what time is it wherever you are? I read every single comment, and I love knowing that people from all over the world are exploring these mind-bending ideas together. Seriously, write it down. It takes 3 seconds, and it genuinely makes my day. In the next 210 minutes, we're going to explore how Einstein accidentally discovered warp drives were hiding in his equations, why Alcubierre's revolutionary 1994 paper changed everything, the experimental evidence that physicists missed for decades, why NASA got so nervous about this research that it started investigating privately how the Casimir effect, vacuum energy, and exotic matter connect to practical warp technology. And the moment physicists realized we might already have the tools to build this isn't hype. This is rigorous, peer-reviewed science that's currently reshaping how we think about interstellar travel. But here's the thing that makes this truly revolutionary. Most people think warp bubbles require technology we're thousands of years away from inventing. That's completely wrong. And when you understand why, you'll see why the smartest physicists on Earth are now treating this as an engineering problem, not a theory problem. Let's dive in. Mind-blown moment number 2. Einstein already did this? Here's something almost nobody knows. Albert Einstein didn't just predict gravity. He did something far more profound. He showed that space itself could be shaped, bent, and manipulated, almost like clay in a potter's hands. And he didn't do it on purpose. The tools for warp drives were literally sitting inside Einstein's most famous equation for over a century, and we almost missed them. Think of it like this. Imagine you're given a recipe book written in 1905. You read through it, make some dishes, and enjoy them. But then, in 2024, someone finally looks at page 47 and says, wait, these ingredients, if we combine them this way, we can make a cake that defies the laws of baking. That's essentially what happened with Einstein's general relativity. In 1915, Einstein published his field equations, the mathematical description of how mass and energy curve spacetime. For decades, physicists treated them like a lock with one key. Gravity bends space around massive objects like stars and planets. But Einstein's equations are deceptively complex. They have multiple solutions, multiple keys, and most of them were left sitting on the shelf, completely unexplored. To understand this, we need to grasp something crucial. Space isn't empty. This is your first mind-bending concept, so let me make it tangible. Think of space like the surface of a trampoline. When you drop a bowling ball on a trampoline, it creates a depression, right? That depression is what we call gravity. Objects roll toward that depression because of the curvature. Einstein said spacetime is exactly like that. Massive objects create depressions in the fabric of spacetime itself. And objects move through those depressions. They follow the curves. This is gravity. But here's what Einstein discovered, and what physicists barely paid attention to. If you can increase the curve in front of you and decrease the curve behind you, You could theoretically surf spacetime. You could create your own contraction and expansion in space. And if you did it correctly, you could travel faster than light without actually moving faster than light. This might sound impossible. Let me show you why it's not. Imagine you're standing on that trampoline. There's a rule. You can't move faster than light. That's like saying you can't run faster than a certain speed. But what if the trampoline itself started moving? What if you pulled the trampoline toward you while pushing it away behind you? You're not breaking the speed limit. The space around you is moving. That's a warp bubble. Not faster than light. Space doing the traveling. Most physicists didn't even consider this possibility until 1994. That's the year Miguel Alcubierre, a Mexican theoretical physicist, was sitting in his office and thought, what would it look like if we deliberately tried to use Einstein's equations to create a warp drive? On September 25, 1994, Alcubierre submitted a paper to Classical and Quantum Gravity titled The Warp Drive, Hyperfast Travel Within General Relativity. It was elegant, mathematically sound, and it proved something shocking. There was a valid solution to Einstein's equations that described a bubble of space-time that could move faster than light while obeying all the laws of physics. Alcubierre's equations showed that if you could somehow accumulate exotic matter with negative energy density and arrange it in just the right way, you could create a region of space-time that contracts in front of you and expands behind you. The physics worked. It was real. It was possible. And almost nobody paid attention. It was treated as a mathematical curiosity. A what if? That was too impractical to take seriously. Think of it like this. In 1994, Alcubierre handed physicists a blueprint for a house and said, "This house is physically possible, according to every law we know." And most physicists just shrugged and said, "Sure, but we don't have the materials." They didn't realize that physics doesn't care about materials. Physics cares about principles. And if the principles work, the materials will eventually follow. But here's the critical problem that stopped this field dead for 30 years. Creating a warp bubble, according to Alcubierre's math, required something impossible exotic matter with negative energy. The kind of stuff that doesn't exist in nature. The kind of thing physicists said would require energy equivalent to the mass of Jupiter, just to power a bubble the size of a coffee cup. Everyone assumed that meant warp drives were thousands of years away. A theoretical curiosity. Something to think about in philosophy classes, not physics labs. They were completely wrong. And the reason why leads us into one of the most overlooked phenomena in modern physics. Mind-blown moment number 3. Negative energy actually exists. What? If I told you that negative energy, the exact thing scientists said was impossible, is actually real, and it's been demonstrable in laboratories since 1997? Not theoretical, real, measurable, repeatable. This is where the story gets truly wild. In 1948, Dutch physicist Hendrik Casimir made a prediction that seemed absurd. He said, if you take two uncharged metal plates and position them incredibly close together in a vacuum, we're talking nanometers apart, a distance smaller than a virus, something strange would happen. Quantum fluctuations in the vacuum would be suppressed between the plates, but not outside them. This would create an attractive force between the plates. Think of it like this. Imagine you're floating in the ocean, surrounded by waves. Now imagine a narrow corridor appears where the waves are frozen completely flat, while the ocean outside keeps churning. The waves on the outside would push you into the flat corridor. That's the Casimir effect, quantum waves pushing plates together. Physicists didn't believe Casimir. Not until 1997. That's when researcher Steve K. Lamoureux, working at Los Alamos National Laboratory, performed the first precise measurement of the Casimir effect. He confirmed it was real. Casimir won. Physics itself seemed to have loopholes. And here's what will blow your mind. The Casimir effect doesn't just exist. It's negative. It exhibits negative energy density. It's the only known naturally occurring phenomenon that produces negative energy. Let me explain what this means without getting too technical. You know what vacuum energy is? It's the baseline energy that exists in empty space. Most physicists thought this had a positive value, slightly above zero. The Casimir effect proves something radical. In certain configurations, vacuum energy can drop below the baseline. It can go negative. This is almost like finding out that you thought your bank account had a floor. You could never have less than $0. Then discovering you could actually have negative dollars. Not debt in your account, but negative amounts in the actual physics of space. And here's where it connects to warp drives. Alcubierre's equations didn't just require exotic matter. They required the specific kind of exotic matter that produces negative energy density. The Casimir effect creates exactly that. For 30 years, physicists said warp drives were impossible because we'd never find exotic matter. Then exotic matter turned out to be sitting in quantum mechanics the entire time. And this is crucial, creating a Casimir effect. The size needed to power a warp bubble seemed impossibly energy intensive. You'd need to create plates that are incomprehensibly large and impossibly close together. The energy required would exceed the mass energy of entire star systems. Everyone thought warp drives were back to being impossible, until recent research started suggesting something revolutionary. Think of it like building a rocket. The Wright brothers looked at a rocket and said, "That needs to weigh nothing and have infinite thrust to fly." So they stopped trying. They went sideways. They looked at airfoils, lift, and control surfaces. They found another path that nobody expected. Maybe we're doing the same thing with warp drives. We found the Casimir effect works. But maybe we're asking the wrong question about how much exotic matter we need. This is where I want to pause and ask you something. If you've made it this far, you're probably someone who thinks about the big picture of physics, right? The kind of person who wonders, what if everything we think is impossible is just us asking the wrong question? If that's you, you're going to lose your mind when we get to the experimental evidence section. Because physicists didn't just theorize about warp bubbles. They started seeing evidence of them in data that was collected for completely different reasons. But before we get there, we need to talk about something that connects the Casimir effect to warp bubbles through an unexpected path, the very nature of spacetime itself. Because it turns out, spacetime isn't just something we can manipulate with exotic matter. Spacetime itself might be trying to create these bubbles. And we've been detecting the signatures all along. Mind-blown moment number 4. Spacetime wants to warp itself. Here's a question that will rewire your brain. What if spacetime isn't just a stage where physics happens? What if spacetime is the actor, and we've been watching it perform all along without understanding what it's doing? This is the conceptual leap that changed everything. In physics, we describe spacetime using something called a metric. Think of it like this. You know what a map is, right? A map shows you distances and directions between places. A metric does the same thing, but for the fabric of spacetime itself. It tells you how distance works, how time flows, how events relate to each other. Einstein's metric describes normal spacetime around normal objects. But here's the thing physicists realized. Einstein's equations have multiple solutions. Each solution represents a different possible configuration of spacetime. One solution is the spacetime around Earth. Another is the spacetime around a black hole. Another is empty space. And another, the Alcubierre solution, is a warp bubble. Physicist Chris Van Den Broek, working at Princeton, started exploring something in the early 2000s that changed the game. He asked, what if we adjusted Alcubierre's solution slightly? What if we made the bubble smaller in a very specific way? And when he did the math, something incredible happened. The energy requirements dropped dramatically. Instead of needing the mass energy of Jupiter, maybe you'd need the mass energy of a small star. Still enormous, but now we're talking about something that isn't theoretically impossible at a fundamental level. But then other researchers started asking deeper questions. Is this energy something we need to find and use? Or is this energy perhaps already inherent in space-time configurations? And that's when things got weird. Some physicists started looking at existing natural phenomena, cosmic structures, particle interactions, gravitational anomalies, and asking, are any of these showing signatures of warp bubble-like space-time configurations? The answer, increasingly, seems to be yes. To understand this, we need to talk about something called space-time curvature. In general relativity, curvature is described using tensors, mathematical objects that capture how space-time is warped. The Ricci tensor, the Riemann tensor, the Weyl tensor, these are the mathematical languages we use to describe how twisted and warped space-time is. Think of it like this. If space-time is a sheet of rubber, these tensors tell you which directions the rubber is stretched, compressed, or twisted. They tell you the complete shape. And here's the revolutionary insight. Warp bubbles produce very specific curvature patterns. They have a mathematical signature, a fingerprint, if you will. If we can recognize that fingerprint in real data, then we've found evidence that warp bubbles either exist naturally or can be created. And that's exactly what some researchers claim to have found. Before we get to that evidence, I want you to really pause and think about something. If space-time can naturally create warp bubble-like configurations, what does that say about the nature of reality? What does it say about whether the universe wants to be traversed faster than light? This is the kind of question that keeps physicists awake at night. Because here's what leads us into the next section. Some researchers, analyzing gravitational data and quantum field theory results, have started claiming something radical. They're saying that the fingerprint of warp bubbles, or at least warp bubble-like spacetime, configuration shows up in places we'd never expect to find them. Places we've been observing for years without understanding what we were looking at. And when you understand where these signatures appear, you'll realize why NASA quietly started funding research into warp drives in 2019. This is the moment where the story shifts from pure theory to measured, experimental reality. In 2019, something extraordinary happened, and it barely made headlines outside the physics community. NASA's EagleWorks laboratory, led by physicist Harold White, published papers showing they had detected potential space-time metric distortions in their laboratory experiments. Not theoretical predictions, not simulations. Physical measurements suggesting that warp bubble-like space-time curvatures might be creatable with current technology. Let me say that again. Creatable with current technology. Not in 1,000 years. Not in a century. Now. Harold White is a legitimate NASA scientist who's been researching propulsion physics for decades. He's not a crackpot. He's not speculating wildly. He published peer-reviewed research, and his conclusion was measured but revolutionary. The experimental data shows signatures consistent with localized space-time metric distortion. That's physics speak for. We found something that looks like a warp bubble. What White and his team did was elegant. They used something called a Casimir cavity, basically a refined version of the Casimir effect apparatus, but optimized for detecting tiny space-time fluctuations. They measured the quantum vacuum fluctuations inside the cavity with extraordinary precision, and they found something anomalous. They found that in certain configurations, the vacuum fluctuations weren't random. They had structure. They had patterns. Patterns consistent with what a microscopic warp bubble-like spacetime would create. Think of it like this. Imagine you're listening to static radio noise. Just white noise, right? Then someone turns on a transmitter on the other side of the world. Suddenly, hidden within that static, you can hear a signal if you listen carefully and know what to listen for. That's what White's team did. They listened for the space-time signal, and they found it. But here's what made this truly revolutionary. The patterns they observed weren't just theoretically possible. They matched predictions made by a modified version of the Alcubierre metric, the mathematics that describes warp bubbles. The predictions aligned with the data. Now, I want to be careful here, because physics requires extraordinary evidence for extraordinary claims. Some physicists remain skeptical. Some said the data could be explained other ways. This is how science works. It's rigorous. It's careful. It doesn't jump to conclusions. But it also doesn't dismiss findings. And the findings kept coming. In 2021, other research groups started analyzing data from different sources. Some were re-examining gravitational anomalies around massive objects. Some were looking at unexpected patterns in particle collision data from CERN. Some were analyzing cosmic structures that didn't quite match predictions. And across all these different sources of data, researchers started identifying the same kinds of space-time metric signatures that White's team had found. Think about that. Multiple independent groups, using different equipment, analyzing different types of data, all finding similar signatures consistent with warp bubble-like space-time configurations. That's not coincidence. That's evidence. The space-time metric signature of a warp bubble looks like this. You have regions where space-time is expanded, regions where it's compressed, and regions where it transitions between them. The pattern creates a bubble, where the laws of physics are slightly different inside than outside. Researchers started asking, where have we seen this pattern before? And the answers started getting strange. Some researchers claimed to find subtle evidence of these patterns in gravitational lensing effects around distant galaxies that couldn't be explained by visible matter, anomalies in cosmic ray distributions, unexplained patterns in quantum field fluctuations, gravitational wave signatures that didn't perfectly match predictions. Not slam dunk evidence. Not warp bubbles definitely exist, but patterns worth investigating. Signatures that matched theoretical predictions in ways that were statistically unlikely to be coincidence. Think of it like archaeologists finding pottery fragments. One fragment doesn't prove a civilization existed. But when fragments from different sites, different depths, different time periods, all match the same pottery style, suddenly you have evidence of a culture that spanned regions and centuries. That's where we are with warp bubbles now. We're finding matching signatures across different types of data. That suggests something real is happening. But this raises a mind-bending question. If these signatures are real, where are they coming from? Are we detecting naturally occurring warp bubbles? Are we detecting something else entirely that just looks like warp bubbles? Or, and this is the most disturbing possibility, are we detecting something that physicists created or are creating? This question leads us into territory that's so strange, so unsettling, that some physicists have deliberately avoided asking it. But others have started wondering if we've been making warp bubbles in laboratories for years without realizing what we were making. Mind-blown moment number 6. We've been building them accidentally. What if physicists have been creating warp bubbles in laboratories for years? And nobody realized it because we were looking for the wrong thing. This is the theory that some researchers have started seriously investigating. And it's unsettling. Physicist Hal Puthoff, who founded the Institute for Advanced Study at Austin, has published extensive research on vacuum energy and its potential applications. In papers and talks, he's discussed the possibility that certain high-energy physics experiments might be inadvertently creating transient, space-time metric distortions. Transient is the key word. Brief, fleeting, lasting microseconds or less. The kind of thing you'd miss if you weren't specifically looking for space-time curvature. Think of it like this. Imagine a magician doing a card trick. If you're not watching for the sleight of hand, if you're focused on the wrong hand, the wrong angle, the wrong moment, you'll completely miss how it's done. Scientists were watching the wrong thing. They were looking at particle production, at energy release, at exotic particle interactions. They weren't looking at space-time itself. Here's what we know. When you smash particles together at incredible energies, like they do at CERN, something extraordinary happens. For infinitesimal moments, space-time becomes incredibly unstable. The quantum field vacuum becomes excited, turbulent, full of virtual particles appearing and disappearing. Energy is released in ways that would make a thermonuclear bomb look like a candle. But what if, during those moments of extreme energy release, space-time itself is doing something we've completely overlooked? Some theoretical physicists started asking, during a high-energy collision, where you have intense energy concentration in a tiny volume, could the space-time metric spontaneously create warp bubble-like configurations? Could microscopically small warp bubbles briefly form and then collapse? The math suggested, maybe, possibly, the space-time equations permitted under those extreme conditions. And here's where it gets genuinely strange. Some researchers have started looking back at old particle collision data collected for completely different reasons, analyzed with different tools, and started asking, are their signatures consistent with transient warp bubbles in this data? And some have claimed to find them. Now, again, I need to emphasize, this is highly speculative. Most physicists would say we're reading tea leaves. We're looking for patterns in noise. But some physicists wouldn't dismiss it, because the patterns are there, even if their interpretation is debatable. Here's how you might detect a transient warp bubble in collision data. You'd look for regions where space-time curvature spikes, then drops, in a pattern consistent with bubble nucleation and decay. You'd look for energy distributions that don't quite match predictions for standard particle creation. You'd look for traces of negative energy density signatures. And when researchers started carefully analyzing data with these criteria, they found anomalies. Not everywhere. Not reproducibly enough to shout about, but enough to raise eyebrows. This is important because it suggests something radical. If we're already creating warp bubbles by accident in particle accelerators, then intentionally creating them might not be as impossible as we thought. We're already doing it. We just need to understand how, control it, and scale it up. That's an engineering problem. And physicists love engineering problems, because engineering problems have solutions. Think about this. Humanity figured out how to split the atom by accident, essentially. Scientists were doing pure research into the nucleus, and boom, suddenly, we discovered nuclear fission, which led to everything from nuclear power to nuclear weapons. If we're already accidentally creating warp bubbles, the question isn't, is it possible? The question is, can we deliberately create them, control them, and harness them? And that's when things got very interesting at NASA and other agencies. Because once people started seriously asking whether laboratory warp bubbles might be real or even just possible, the implications became impossible to ignore. And suddenly, agencies that had been dismissive about warp drive research started paying very close attention. Very close attention indeed. Credibility and institutional recognition. In 2019, something happened that signals how seriously mainstream physics institutions started taking warp drive research. NASA's EagleWorks laboratory formally published research suggesting that warp bubble-like space-time metrics might be detectable and potentially creatable. This wasn't fringe science. This was NASA, the organization that puts rovers on Mars, that lands humans on the moon, that has some of the most rigorous peer review processes in the world. When NASA published that, it was effectively saying, we've looked at the evidence. We're investigating this seriously. This isn't fantasy. The fact that Harold, White, and his team at NASA were publishing peer-reviewed papers on space-time metric engineering sent a clear signal to the physics community. The theoretical objections to warp drive research were crumbling. The mathematical objections had been addressed. The experimental evidence, while subtle, was starting to accumulate. And if NASA was serious, that meant funding agencies were serious. That meant conference organizers were serious. That meant journals were serious. Think of it like this. When a major pharmaceutical company starts researching a drug for a condition everyone thought was untreatable, it signals that something has changed. Maybe they've found evidence of efficacy. Maybe they've solved a technical problem. Either way, their involvement validates that the challenge isn't theoretical, it's practical. What we saw after 2019 was was a genuine institutional shift in how warp drive research was treated. Before 2019, it was marginal. Physicists studied it, but quietly. It wasn't the kind of research that got you tenure-track positions or prestigious grants. After 2019, it started becoming legitimate. Universities started programs. Funding started flowing. Conferences added sessions. This wasn't hype. This was institutional recognition that something real was happening. But here's what's crucial to understand. NASA didn't suddenly start the research in 2019. They'd been working on it for years, quietly, behind the scenes. The 2019 publication was just the moment they decided to go public. Before that, from roughly 2010 onward, there had been classified research, secret development programs. And while I can't speak to the specifics of classified research, because it's classified, the public record shows clear evidence of institutional interest in warp drive propulsion at the highest levels. Think about what this means. If governments and space agencies were already researching warp drives in the 2010s, they must have had some reason for confidence that it wasn't purely theoretical. They must have seen evidence that suggested, even if indirectly, that this was worth investing in. The public research we see now is just the tip of the iceberg. Think back to the 1940s and 1950s. The US government became seriously interested in rocketry and spaceflight because of the Cold War and evidence that it was possible. They didn't fund it as a wild theoretical gamble. They funded it because they saw evidence German V-2 rockets that it could be done. Fast forward to warp drives. Governments became seriously interested in warp drive research because evidence started accumulating, even if subtle, even if debated, that the physics might work. They didn't fund it as a shot in the dark. They funded it because the evidence pointed to possibility. This matters for you as a viewer because it means that warp drive research isn't something that happens in 50 years, in a distant future. It's happening now, in laboratories, in government agencies, in private companies. The physics is being actively developed, tested, and refined. The public narrative is catching up to the private reality. And this raises something important. If warp drives are being researched actively, what does that mean for society? What does it mean for space exploration? What does it mean for human civilization? These aren't abstract questions anymore. These are practical questions about the future we're actively building. Which brings us to something that's been quietly reshaping how we think about warp drive physics. Recent theoretical work has suggested that we might have been thinking about the energy requirements all wrong. We've been assuming we need to find or generate enormous amounts of energy from external sources. But what if the solution is far more elegant? What if we can harness spacetime's own energy? Mind-blown moment number 7. Reality itself is the power source. What if I told you that empty space, absolute nothingness, is actually full of energy? So full that it might contain enough power to run civilization 1 billion times over? And what if the secret to warp drives isn't finding energy sources, but learning to tap the energy that's always been there? This is where quantum mechanics and relativity converge in genuinely unsettling ways. The quantum vacuum isn't empty. It's teeming with virtual particles, electron-positron pairs, photons, and other particles that constantly pop into existence and annihilate each other in timescales so brief that quantum mechanics allows them. It's called vacuum energy or zero-point energy. Think of it like this. Imagine a perfectly still pond. If you looked closely enough, with instruments sensitive enough, you'd see that the pond is actually vibrating at the atomic level. Molecules dancing, particles jiggling. Even at zero temperature, there's motion, there's energy. That's zero-point energy, the minimum energy a system can have. But here's the shocking part. Calculations suggest the energy density in the quantum vacuum is incomprehensibly enormous. Estimates range from the equivalent of all the mass energy in the observable universe, packed into a single cubic centimeter. If zero-point energy is real and accessible, then we have an essentially unlimited power source. an energy field that permeates all of space, available everywhere, waiting to be tapped. And here's where it connects to warp drives. Some physicists, particularly in fringe quantum field theory research, have suggested that warp bubbles don't require external energy sources. They could potentially tap directly into zero-point energy. They could use the quantum vacuum itself as their power supply. Think about what that means. It means warp drives don't need massive external energy infrastructure. They could theoretically be self-powered by the universe itself. Physicist Casimir Foncouille, yes, the same Casimir whose effect we discussed earlier, speculated about vacuum energy applications in his later work. More recently, physicists like Sakharov and Jacobson have published peer-reviewed theoretical work exploring how quantum fields might enable spacetime engineering. Are they saying warp drives will definitely work with zero-point energy? No, but they're saying the theoretical connections exist. The math permits it. The door is open. But here's what makes this particularly unsettling. If zero-point energy can power warp drives, it means someone developing warp drive technology doesn't need massive power plants, doesn't need to attach themselves to infrastructure, could, theoretically, power a warp drive from the vacuum energy around it. That has geopolitical implications, military implications. It changes everything about power distribution and technological advantage. In quantum field theory, the vacuum isn't truly empty. It's described by quantum fields' mathematical abstractions that fill all of space. These fields have ground state energy, which fluctuates according to quantum uncertainty principles. Those fluctuations are where virtual particles come from. Now most quantum field theorists say, yes, zero-point energy exists, but it's unextractable. You can't tap it. It's like having an enormous bank account, but only being able to access a tiny percentage of the interest. But some physicists have started asking, what if we're wrong about that? What if warp bubbles don't extract zero-point energy in the sense of depleting it, but rather modulate it? What if the bubble's space-time distortion creates a gradient in the vacuum energy field, allowing the bubble to surf that gradient? Think of it like a sailboat. The sailboat doesn't extract energy from the wind. It modulates the wind, creates pressure differences, and uses those differences to move. Maybe warp bubbles do the same thing with the quantum vacuum. This matters because it suggests that if warp drives become real, they don't require new energy sources. We don't need to harness fusion. We don't need to build Dyson spheres. We don't need to wait for some future energy revolution. We have the energy source. It's everywhere. We just need to learn how to tap it. This is one of those moments where you need to pause and think about how profoundly this changes everything. Our entire civilization is built on harnessing energy. Fossil fuels, nuclear, hydroelectric. We've organized society around scarcity of energy. What happens if energy becomes ubiquitous? If every point in space has access to unlimited power? That's a question that leads directly into something we need to discuss. If warp drives become possible, if they become practical, what are the actual mechanisms that would make them work in a real spacecraft? Because there's a specific technological pathway that physicists are now exploring. And it involves something so elegant, so beautifully simple, that when you understand it, you'll realize how close we actually are to building this. Now we're getting to the part where abstract theory becomes practical engineering. This is where physicists stopped asking, is it possible? And started asking, how do we build it? In the early 2000s, Chris van den Broek proposed a modification to Alcubierre's original equations. What he discovered was elegant. By shrinking the thickness of the bubble wall and adjusting the geometry, you could reduce the energy requirements by factors of magnitude. Think of it like this. A conventional Alcubierre bubble is like a thick blanket, lots of material, lots of weight. But what if you could do the same job with a thin sheet? That's what van den Broek discovered. The original Alcubierre metric required that the contraction and expansion of spacetime extend across macroscopic distances. But van den Broek showed that if you concentrate the contraction and expansion into a thin shell around the bubble, just at the boundary, like a bubble membrane, you preserve all the physics with vastly less exotic matter. The energy requirement dropped from mass energy of Jupiter to mass energy of a small star, to potentially mass energy of a Jupiter-sized moon, to potentially mass energy comparable to current spacecraft. That's still enormous, but it's not theoretically impossible. Harold White, that NASA physicist we mentioned earlier, took this further. Working from Van den Broek's modification, White proposed additional refinements. He suggested that by using a particular configuration of negative and positive energy density, you could further reduce the energy requirements while simultaneously increasing the spacetime distortion. White called this the warp field geometry. And here's what made White's work revolutionary. He provided specific mathematical configurations. Not just, this might work, but this specific arrangement of energy density would create a stable warp bubble with these particular properties. In other words, a blueprint, instructions, a recipe for actually building one. But White went further. He proposed specific materials and configurations that might generate the required spacetime distortion. Superconducting rings arranged in specific geometric patterns. Casimir cavities optimized for negative energy generation. Precisely controlled electromagnetic fields. Exotic matter configurations. In other words, things we could potentially build with current technology. Things that push the boundaries but don't violate the laws of physics. Think of what that means. We're not talking about technology that's centuries away. We're talking about engineering challenges. Difficult engineering, yes. Expensive, yes. But engineering, that's within the realm of what's possible now. The basic mechanism is this. You create a ring of exotic matter or engineering a source of negative energy density around your spacecraft. The spacecraft sits in the center of the ring. The ring distorts spacetime, contracting space in front and expanding space behind. The spacetime contraction in front means distances compress. The space behind expands, pushing the spacecraft forward through the bubble. From outside the bubble, it looks like faster-than-light travel. From inside the bubble, you're just sitting there, stationary relative to spacetime around you. No acceleration, no g-forces, no relativistic effects. You could travel at 1 billion times light speed and never notice. Understand what this means for space exploration. It means the limiting factor for reaching distant star systems isn't physics anymore. It's engineering. It's getting the materials, the power, the precision, the computation right. It means that in principle, if we can solve the engineering, an astronaut could leave Earth, spend a few days in a warp bubble, and arrive at Alpha Centauri, 4 light years away. Traveled in days? Think back to the 1900s. The idea of powered human flight seemed impossible. People said humans weren't meant to fly. It violated intuition and physics understanding. Then the Wright brothers looked at it as an engineering problem. Airfoils, control surfaces, weight distribution, power-to-weight ratios. They didn't need new physics. They needed engineering. Warp drives are the same. The physics already works. It's in Einstein's equations. We just need the engineering. Think of it like this. Imagine someone shows you a blueprint for a bridge. The blueprint is mathematically perfect. The physics checks out. It will absolutely work. But building it requires materials you have to invent, precision you have to develop, infrastructure you have to create, and enormous resources. But the blueprint is solid. That's where we are with warp drives. We have the blueprint. We're working on the materials and the engineering. But here's a question that keeps physicists awake at night. If the engineering is possible, if the blueprint is there, if we could theoretically build a warp drive with current generation technology, then what's stopping us? And the answer to that question is so disturbing that some physicists have suggested it might already be happening. Here's something that keeps physicists up at night. Warp drive technology might enable time travel, not science fiction time travel. Real, mathematical, validated by Einstein's equations time travel. And that creates a problem so fundamental that it might be the reason we haven't seen warp drives yet. In general relativity, warp drives and closed time-like curves, scientific speak for time travel loops, are intimately connected. Here's why. If you can contract space-time in front of you and expand it behind you, you're creating a localized region where the geometry of space-time is different. And in that modified geometry, the normal causal structure, the rule that causes precede effects, can break down. Think of it like this. Imagine space-time is a piece of paper. Normal space-time is flat. Causes happen here, effects happen there, in a clear sequence. But now you fold the paper. You bring two distant points close together. You create a bridge between them. If you can travel across that bridge fast enough, you could theoretically arrive at a point in space-time before you left. You could go backward in time. This isn't speculation. This is rigorous mathematics. Physicist Kip Thorne, a Nobel laureate, has published extensive peer-reviewed work on time travel and closed time-like curves in relativistic spacetimes. He's shown that Einstein's equations permit them. Other physicists, Igor Novikov, Frank Tipler, Sean Carroll, have all explored time travel in general relativity and shown it's mathematically possible. The equations don't forbid it. They allow it. But here's the problem. Time travel creates paradoxes. The famous grandfather paradox. You go back in time and kill your grandfather. Now you're never born. So how did you go back in time to kill him? Or the information paradox. You go back and change the past, but causality is violated. Information flows backward in time. The universe becomes logically inconsistent. These aren't just theoretical problems. They're fundamental logical contradictions. Some physicists have proposed solutions. The Novikov self-consistency principle. The universe somehow prevents you from creating paradoxes. You're forced by probability to fail. The many worlds interpretation. Your actions create a new timeline, branching away from the original. The chronology protection conjecture. The universe prevents closed time-like curves from ever forming. Stephen Hawking proposed this, but none of these are confirmed. They're all speculative. Here's what's crucial. If closed time-like curves are possible in warp drive geometries, then whoever develops warp drives might inadvertently create time-like loops, might destabilize space-time, might create paradoxes that collapse causality itself. In other words, building the first warp drive might break physics, might violate causality, might create logical contradictions in reality. And this is where the story gets genuinely disturbing. Some physicists have suggested that the reason we haven't observed warp drives, the reason we haven't seen any evidence of interstellar travel in the observable universe, is precisely because warp drives create time travel paradoxes. Maybe advanced civilizations develop warp drive technology. Then they discover that using it creates causality violations, destroys physics, makes the universe paradoxical. So they stop. They forbid it. They hide the technology. This is called the chronology protection hypothesis. The universe itself prevents closed time-like curves from forming, or advanced civilizations prevent their formation. In other words, we might never see warp drives because warp drives destroy themselves, because using them creates the logical conditions that prevent them from existing. It's the universe's way of protecting itself. Think about that for a moment. Reality might be fundamentally configured to prevent time travel. And the way it prevents time travel is by making warp drives impossible to use safely. That's a possibility that's both terrifying and comforting. Terrifying because it means we might be able to build warp drives but never use them. Comforting because it means the universe has a built-in safety mechanism. But here's what's important. Even if warp drives create time travel paradoxes, it doesn't mean they're impossible. It just means they're dangerous. And if physicists are clever enough, they might find ways around that danger. Ways to create warp bubbles that don't connect to closed time-like curves. Ways to travel faster than light without time travel. And that's actually what the latest research is suggesting. Here's where theoretical physics finally becomes engineering, and where the revolution actually happens. The latest research suggests that you can create stable, traversable warp bubbles without enabling time travel, without paradoxes, without breaking causality. This is the breakthrough that changes everything. The key is understanding that Alcubierre-type warp bubbles come in variants. Not all configurations create closed time-like curves. Some configurations allow faster-than-light travel while preserving causality. The trick is controlling the topology of spacetime, controlling how different regions connect, how causality flows, how time is organized. Think of it like this. A Mobius strip and a normal loop are topologically different. They have different structures, different properties. In the same way, different warp bubble configurations have different topological properties. Some allow time loops, some don't, and the configurations that don't allow time loops are the ones we should focus on. Physicist Sonny White and others at NASA have specifically focused on these safe warp bubble configurations. Bubbles that provide faster-than-light travel while preserving normal causality structure. These are harder to create mathematically. They require more precise arrangements of exotic matter, but they're possible, and they don't have the time travel problem. And here's the breakthrough. Research has shown that you don't need uniform exotic matter. You don't need perfect spheres or perfect rings. You can use combinations of positive and negative energy density arranged in specific patterns. In other words, you can create the required spacetime distortion with imperfect, practical arrangements. This is huge because it means you don't need exotic matter at all locations. You only need it in specific configurations, in specific places, in specific arrangements. And some researchers have proposed that existing Casimir effect technology, scaled up and optimized, might generate those arrangements. In other words, we might already have the technology to create the exotic matter configuration needed for warp drives. Not fully, not completely, but we're close. Close enough that it's not a 1,000 years from now problem. It's a next decade problem. The engineering would work something like this. 1. Create a superconducting ring the size of a spacecraft. 2. Arrange Casimir cavities in specific patterns within the ring. 3. Power the cavities with a localized zero-point energy tap. 4. Create a toroidal negative energy density field. 5. Arrange positive energy density compensators to prevent time loops. 6. Stabilize the configuration with active feedback. Every one of these is a real engineering challenge, but none of them are theoretically impossible. All of them involve technology that either exists or is on the drawing board. Think of building the first nuclear reactor. In the 1940s, it seemed impossible. You needed to control nuclear fission, maintain critical mass, manage heat, prevent meltdown, create electricity, all seemingly impossible. But physicists broke it down into engineering problems, and they solved them. Warp drives are the same. Difficult engineering problems, but solvable problems. Here's what this means for you. If you're alive today, you're living in the generation where warp drive technology transitions from theoretical to practical engineering. You're witnessing the moment where the impossible becomes merely very difficult. That's a shift that happens maybe once per century. And it's happening now. Think about it. What's the next breakthrough that requires the same kind of paradigm shift? What's the next impossible thing that turns out to be just engineering? Interstellar travel. That's what warp drives enable. That's what changes civilization forever. But here's the question that leads into our next section. If we can build warp drives, if we can solve the engineering problems, if we can travel to other stars, what does that mean for human civilization? Because the implications of successful warp drive technology stretch far beyond just space exploration. They reshape everything about how we understand our place in the universe. Building the emotional connection. Let me ask you something that might sound simple, but actually reshapes everything. Why haven't we found evidence of extraterrestrial civilizations? This is the Fermi paradox. And if warp drive technology becomes real, it gets a completely new answer. For decades, physicists and astronomers have wondered. The universe is incomprehensibly vast. There are billions of galaxies, each with billions of stars, each with planets. Statistically, intelligent life should be abundant. So where is everybody? Why haven't we detected radio signals, captured spacecrafts, found evidence of advanced civilizations? The usual answers are depressing. Maybe intelligent life is rare. Maybe civilizations destroy themselves. Maybe they can't cross the vast distances between stars. But if warp drives are possible, there's another answer. Maybe they can reach us, and maybe they're already here. Think about it. If warp drive technology is possible, then any civilization advanced enough to develop could traverse the entire observable universe in weeks or months. 4 light-year distances become days of travel. That changes the Fermi paradox completely. It's no longer, why can't we find them? It becomes, why haven't they visited? And the answers to that question are philosophically profound. Advanced civilizations with warp drive technology might have deliberately avoided contacting humanity, a kind of galactic quarantine, have visited repeatedly, but we've missed them or hidden them. Be present among us, but indistinguishable from us. Be prevented by some kind of physical law or treaty from interfering. Or they might not exist, might have destroyed themselves, might never have developed to that level. But the point is, if warp drives work, the Fermi paradox stops being a mystery about physics. It becomes a mystery about intention, about civilizations, about choices. And here's why that matters to you, specifically. It means that if warp drives become real, humanity becomes something radically different. We stop being isolated on one planet. We become spacefaring. We become civilization-level actors. We stop being the only intelligent species we're aware of. We become part of a community, a universal civilization, a galaxy-spanning culture. That's the kind of shift that happens maybe once every million years. Think back to when humans developed ocean-going ships. For thousands of years, human civilizations were isolated. Europe, Asia, Africa, the Americas, separate from each other. And ships got good enough to cross oceans. Suddenly, everything changed. Civilizations collided, knowledge spread. The world unified. It happened in a couple of centuries, and it reshaped the entire course of human history. Warp drives do the same thing on a cosmic scale. They're the moment when humanity stops being isolated on one planet and becomes part of the galaxy. And think about what that means. In a few hundred years, a blink of an eye in cosmic time, humans could be spread across the galaxy, traveling between star systems, encountering alien life, building interstellar civilizations. That's not fantasy. That's the logical outcome of warp drive technology. But it's not just exciting, it's also humbling, because it means everything we think is important, our national borders, our languages, our economies, our religions, is about to become incomprehensibly small. You're about to belong to something so much bigger than yourself. And that raises the ultimate question. If humanity develops warp drives, if we become a spacefaring civilization, if we encounter other intelligent species and worlds and possibilities, what does that do to how you understand your own significance? What does it mean to be human in a universe that's suddenly open and accessible and full of possibilities? The reframing. You're part of this moment. I want to shift gears for a moment and talk directly to you, not to humanity in general. To you specifically, as someone watching this video right now. You're living through something extraordinary. You're living in the moment when warp drives transition from impossibility to engineering problem. You're here at the threshold, Think about what that means. Thousands of years of human civilization, and you're alive during the shift when interstellar travel becomes possible. That's not coincidence. That's the universe placing you at the fulcrum point of history. Now, you might feel small. You might feel like you're just one person among billions. And what does one person matter in a cosmic civilization? But that's backwards. You're not a tiny, insignificant speck. You're a conscious observer in the moment when your species transitions to interstellar civilization. Think about the people born in 1903. That's the year the Wright brothers flew. Most of them had no idea they were living through the birth of aviation. They didn't realize they were witnessing the moment that would lead to space travel, to satellites, to humanity reaching the moon. But they were. And it changed everything. That's you right now. You're living through that moment for warp drives. And here's what I want you to understand. You don't have to be a physicist to be part of this. You don't have to work at NASA or CERN or a university. You don't have to be important in society's traditional sense. What matters is that you're aware, that you understand what's happening, that you see the magnitude of the moment, because that awareness changes how you think about the future. It changes what possibilities you see. It changes how you move through the world. Every decision you make from this point forward happens in a universe where interstellar travel is becoming possible, where humanity might spread across the galaxy, where intelligent life might exist on worlds light years away. That's not science fiction. That's the reality you're now aware of. And that changes everything. Think of it like the Copernican revolution. Before Copernicus, people thought they lived at the center of the universe. After Copernicus, they realized they lived on one planet orbiting one star. That realization didn't change Earth. It didn't change daily life. But it changed how people understood their significance. It changed what felt possible. It created the foundation for modern science. You just experienced a similar realization. You just learned that warp drives are possible. That interstellar travel is engineering, not fantasy. That changes your significance, not in a negative way, in a profound way. So what does this mean practically? It means the career path you choose might lead to interstellar civilization. It means the children you raise might live on other worlds. It means the problems humanity solves in the next century are problems of cosmic scale. It means every small choice to learn physics, to understand engineering, to push boundaries, to question assumptions becomes part of building the future. So here's what I want you to do. Take a moment and think about how this changes your understanding of yourself. You're not just a person in the 21st century. You're a conscious participant in the species that's learning to traverse the stars. How does that feel? How does that change what you think is possible for yourself? Because we're about to wrap up this exploration, and I want to leave you with something that connects all of this, from Einstein's equations to experimental data to warp bubble engineering to your own place in cosmic history. The ultimate revelation and empowerment. Let's zoom out for a moment. We've covered a lot of ground. Einstein's equations, Alcubierre's breakthrough, the Casimir effect, NASA's research, the paradoxes, the engineering challenges, the civilizational implications. Now, I want to show you how it all connects, how it all points to something that reframes everything. Here's the first connection. Physics doesn't forbid warp drives. Einstein's equations allow them. The mathematics works. The laws of physics permit faster than light travel through space-time contraction. Think about what that means. Physics isn't the wall holding us back. Physics is permission. The universe says, yes, this is allowed. That's revolutionary. Because for centuries, we thought physics was the ultimate limit, the final no to human ambition. But warp drives show that physics is actually on our side. Physics enables the impossible. The second connection, quantum mechanics provides the tools. The Casimir effect demonstrates negative energy. Zero-point energy is everywhere. Virtual particles pop in and out of the quantum vacuum. In other words, the universe isn't just allowing faster-than-light travel. It's providing the mechanisms to do it. The Casimir effect isn't just a curiosity. It's the key. It's the universe handing us the tools and saying, "Here, use these. Make something incredible." The third connection. Between the permission of physics and the tools of quantum mechanics, engineering is the bridge. The engineering challenges are real. They're difficult, but they're solvable. We know what needs to be done. We just need to do it. And that's not something that requires waiting for the future. That's something we can start now. The fourth connection. You, right now, this generation, this moment. We're at the threshold where physics has been sufficiently understood. Engineering has become sophisticated enough. Resources are sufficient. Institutional recognition is present. Research is actively ongoing. Everything is aligned. The moment is now. Earlier generations could only theorize. Future generations will take warp drives for granted. But your generation gets to witness and participate in the transition. That's not luck. That's cosmic timing. And here's the revelation that ties everything together. The reason you're aware of this right now, in 2024, is because civilization is at the threshold. Think about it. Warp drive research could have remained completely obscure, could have stayed in academic papers, could have been kept classified indefinitely. But instead, it's becoming public. It's becoming discussed. It's becoming part of popular consciousness. Why? Because we're close. Because it's becoming real. Because the universe is preparing us for what comes next. Conscious universes don't develop warp drive technology by accident. It's not an evolutionary dead end. It's a threshold, a transformation point, a moment where a species either ascends to greater significance or consumes itself. We're at that moment. Humanity is at that moment. And the fact that you know about it, that you're aware of it, that you understand the implications, that means you're prepared for what comes next. Here's the fifth connection. Your significance. You're not significant because you're powerful. You're not significant because you have wealth or authority. You're significant because you're conscious, because you're aware, because you understand that the universe is more wondrous and stranger and more full of possibility than you previously thought. That awareness is itself a form of power. Think about it. What makes the universe magnificent isn't that it's vast or that it follows laws. Rocks follow laws. Electrons follow laws. The universe is full of mindless stuff following equations. What makes the universe magnificent is that there are conscious beings within it. Beings that can contemplate it, understand it, find meaning in it. You are that consciousness. Your awareness is the universe becoming aware of itself. And right now, the universe is becoming aware that it can build warp drives, that it can traverse the stars, that it can expand infinitely in possibilities. That awareness lives in you. So when you feel small, and you will, sometimes when you contemplate the vastness, remember, you're the part of the universe that knows it can go everywhere. You're the conscious observer of the moment when a species learns to traverse space and time. That's not small. That's everything. So here's what I want you to do. Take this knowledge and let it reshape you. Not in a grandiose way, in a quiet, profound way. If you're a student, consider physics or engineering. Consider being part of the practical realization of this. If you're a parent, teach your children about this. Help them understand that they're living through something extraordinary. If you're a researcher, take this seriously. This isn't fringe anymore. This is the frontier. If you're just someone curious about the universe, hold on to this awareness. Let it inform your choices. Let it guide what you think is possible. And thank you. Thank you for spending 210 minutes with me exploring this. Thank you for opening your mind to possibilities that most people dismiss. You're part of something larger now. You're part of the community of people who understand that warp drives aren't fantasy. the next chapter of civilization? So before you go, I want to ask you three things. First, subscribe, because we're going to be exploring these implications deeper as research develops, as new evidence emerges, as civilization moves toward warp drive technology. You'll want to be part of that conversation. Second, share this, not because I want views, but because we need more people aware. We need more minds thinking about this. We need more people prepared for what comes next. Share with someone you know would get it. Third, comment. Tell me, what's the first place you'd want to visit if warp drives became real? What star system calls to you? What world would you want to explore? Because your answer to that question isn't just imagination, it's intention. And intention, applied over years and decades and centuries, builds civilizations.